Okay, let's dive right into this because today we are exploring an absolutely fascinating thought experiment. We're going to look at a Python simulation that actually analyzes the Great Pyramid of Giza as a hypothetical machine. Seriously, it's a predictive model, and it uses wave physics and continuum mechanics to test this massive structural hypothesis. I'll tell you up front, it's highly technical, it's incredibly creative, and it visualizes some seriously intense mathematics.
So it brings up the ultimate question, right? Was the Great Pyramid of Giza a power plant? Now, I want to establish our anchor right here at the very beginning so we're all on the same page. We are analyzing a specific set of simulated mathematical predictions generated by a Python script. We're looking purely at the math of continuum mechanics. We are absolutely not looking at historical proof, and we're not endorsing any alternative history here. We're just looking at a really cool mathematical what-if scenario that tests the very limits of geometry and physics.
Here is our roadmap for this explainer. We've got 4 parts. First, the power plant hypothesis. Second, calculating matrix mechanics. Third, the acoustic funnel effect. And finally, projected power potential. All right, jumping right in. Section 1, the power plant hypothesis, code and caveats. What we are looking at is sourced from a Python script that was designed to test pyramid cavitation and singular value decomposition, or SVD, power potential. Basically, it's a digital blueprint to see if the physical structure of a pyramid could theoretically generate and focus energy.
But before we even look at the numbers, the original code explicitly outputs this warning. Predictive simulation results, simulated predictions, not proof. This is absolutely vital to keep in mind. The creator of the code is being super responsible here, and we are going to match that impartial stance. These are strictly theoretical models, based on structural inputs. It's essentially a playground for wave physics, not an archaeological claim.
Let's move to and see how this builds. Section 2, calculating matrix mechanics, the foundation. To figure out if a structure can generate power, the code first has to calculate exactly how much pressure it can store.
And to do that, the code uses something called the Frobenius norm of the stress matrix. Okay, I know that sounds like incredibly intimidating jargon, but here is what you really need to take away from this. In continuum mechanics, it's just a mathematical way to measure the maximum strain energy density stored in a pressurized medium. Just think of it like a giant, high-capacity energy reservoir holding immense pressure.
And this brilliantly illustrates what happens next. The Python script generates 3 exact singular values, S1, S2, and S3. Look at S1. It is massive, sitting at roughly 1.87 times 10 to the 9th power. These numbers, they represent the raw, unfocused stress matrix variables derived from the structure before any energy is directed or utilized. It's basically the baseline potential.
Which brings us to Section 3, the acoustic funnel effect, directing the force. Because having a massive reservoir of energy doesn't mean much if it just dissipates into the ground, right? The simulation explores how the stepped exterior geometry of the pyramid hypothetically manipulates and focuses this raw energy.
So, when the code calculates the variance distribution of that stress, the results are pretty incredible. Over 94% of the stress tensor is constrained along a single primary axis. Only about 2.8% bleeds off into the secondary and tertiary axes, meaning the simulation predicts that the overwhelming majority of the energy does not dissipate outward laterally. It's pushed strictly along one primary vertical path.
The math outputs this as an anisotropy focus ratio of roughly 16.57 to 1. Think of this ratio like a giant geometric magnifying glass. It takes all that lateral overburden pressure and tightly focuses the energy vector into a single directional beam. And in this specific simulation, that beam is modeled to be directed straight down at a theoretical quartz and mercury cavern interface.
The script even calculates the precise principal shear angle of this focused energy. It pegs it right at negative 144.52 degrees. I point this out because it really highlights the level of granular physics making this predictive model run. It's not just guessing here. It's using the rigid laws of wave physics to track exactly how that theoretical force would behave.
Now, what's really interesting about this next part is how it all connects. Section 4, projected power potential, the final calculation. This is where all those individual variables come together, and the script actually attempts to calculate the real power flex based on the geometry.
The code walks through a highly specific 3-step sequence. Step 1, it takes that total stored stress energy, calculating a Frobenius norm of roughly 1.87 billion. Step 2, it applies that 16.57 to 1 directional anisotropy ratio, which funnels the energy. And step 3, to find the power potential projection, it multiplies that stored stress energy by 2 totally new variables, a driving acoustic frequency and a coupling efficiency factor. Now, to keep the model grounded, the simulation uses highly conservative inputs for that final calculation. It introduces a sub-bass carrier bass driver frequency of just 60 Hz, and for the coupling efficiency, how well the system actually transfers that energy, it assumes a tiny efficiency of just 1.0%.
So the crucial point is the final output. Check this out. Even when scaling down to a mere 1% coupling efficiency and driving it at only 60 Hz, the accumulated strain energy scales into a massive 1.127 gigawatt prediction. Yep, over 1.1 billion watts of theoretical power flux. It provides this crystal-clear mathematical scale for the simulated energy density of this geometric structure. It's wild.
So, summarizing the key structural takeaways from the data, we really see three main things. First, the directional funneling created by that 16:1 ratio actively prevents energy from dissipating outward. Second, the total stress tensor magnitude, that Frobenius norm, acts as a high-capacity energy reservoir. And third, the matrix mechanics show that the inverted stepped geometry functions beautifully as a pressure concentrator, theoretically driving stress straight down into the core interface.
But as we wrap up this data analysis, we have to return to the exact disclaimer coded into the source material. Simulated power potential. Predictions, not proof. This entire exercise, it's just an exploration of matrix mechanics and continuum mechanics applied to a specific shape. We are simply letting the Python script speak for itself, impartially presenting the numbers that the math demands.
Which leaves us with this final thought. When a structural simulation yields a gigawatt-level energy prediction using incredibly conservative inputs, what do these mathematical possibilities reveal about our understanding of theoretical physics and geometric engineering? It's a fascinating application of modern wave physics, and it for sure makes you look at the geometry of massive ancient structures in a completely different light. Hopefully, this breakdown has sparked your curiosity to go look a little deeper into the math of continuum mechanics yourself.